Hey guys, welcome back to the channel. Today we're going to start looking at some multi-phase simulations and specifically the volume of fluid method. We're going to use the volume of fluid technique to model an inkjet printhead and specifically look at the droplet generation from that inkjet printhead. Using the VOF model to model inkjet printheads is still a current active field of research. So there's a lot of new research coming out of ways to improve both the fluid dynamics modeling, as well as experimentation and optimization of printheads. So you can see on the right here, what we're going to look at today is the generation of droplets. It's common to use the VOF model to probe your entire inkjet system and do things like optimizing for new inks, so inks with either a different viscosity or different material properties, as well as optimizing your inlet pressure profiles, so looking at droplet stability, reduction of satellites, or essentially any other system optimization when we're talking about droplet generation. Today we're going to look at aqueous inkjet, so our working fluid is going to be water-based, but you can also do the simulation with liquid metals, nanoparticle inks, different polymers, or essentially any other inkjet printhead that you want to look at. It's common when you're looking at droplet generation and simulation of inkjet printheads to split the domain into two sections. So if we're looking at this simple model on the left, you can see we have an ink chamber with a piezo actuator up top and our nozzle down at the bottom. To generate our pressure profile and to look essentially at a system level, we usually do a single phase simulation of this entire chamber, the nozzle, and the piezo inkjet with one phase simulation. From that, we can develop our pressure profile and understand how our system actuates. And then we can take that pressure profile and apply it to a smaller domain for looking at our multi-phase droplet generation. So today we're just going to look at the multi-phase part in the droplet generation. So what we're going to do is we're going to split this domain about a few millimeters above our nozzle and look at the generation of our droplets by using an implied pressure condition at the top of our domain. So before we get into the model, I'm going to touch a little bit on theory. I believe it's pretty important, especially when you're getting started with the VOF model, to understand a little bit about how it works. So the VOF model is one of the most popular multi-phase simulation models, specifically because it can track interfaces very well and can give very accurate results when you're comparing it to experimental data. The VOF model essentially uses a continuum momentum field across the entire domain. So you can think of it like it calculating a pseudo-fluid across the entire domain. And then we use what's called a fraction function or a volume fraction function to alter our material properties depending on what fluid exists in what cell. In Fluent, if you look at the theory manual, they denote this fraction function as alpha Q. So if we look at alpha Q is equal to 0, it will mean that the cell is completely empty of the Qth fluid. So if we look over on our diagram on the right, we see this cell up here is equal to 0, which means that it is entirely filled with fluid B and none of fluid A. If alpha Q is equal to 1, it means that the cell is entirely full of the Qth fluid. So if we look down here, we have 1, it is entirely fluid A. And if alpha is anywhere between 0 and 1, it means that that cell contains an interface. So this interface is what we're going to be tracking between our two phases. To get our flow properties correct between our two phases, since we're going to have usually a gas and another fluid, we need to alter our material properties depending on the fraction function in each cell. To do that, we use a simple equation down here specifically for the density, but it is the same equation that we would use for viscosity, heat transfer properties like thermal conductivity, or any other material properties. And all we're essentially doing is we're calculating our density, or rho, by multiplying our density of each fluid by the fraction function in that cell. So as you can see here, we have alpha Q multiplied by PQ. So if we look at our diagram again, in this cell where we have 1 or all of fluid A, we're going to multiply the density of fluid A by our fraction function, which is 1. And that means in this cell, the density is going to be equivalent to just the density of our fluid A. And that's where it gets a little bit tricky, is when we look at these cells along the interface where we have fractional fraction functions. So 0.4, 0.2, 0.9. We're going to have to scale our density in these cells according to that fraction function. And this really brings up the most difficult part of the VOF model or multi-phase modeling in general, which is trying to reconstruct this interface. So if we look at a cell here where we have maybe 0.1 and we have this interface just crossing the bottom edge of this cell, it's very difficult numerically to figure out exactly where that cell should be and how it fits into the cells neighboring around it to get an accurate simulation of our interface condition. There's multiple techniques that Fluent uses to do this numerical approximation of our interface. Some of the most popular ones that you'll see are GeoReconstruct, the donor and accepted method, SIXAM, and a few other ones. Today we're going to be using the GeoReconstruct method as it is proven to be one of the most accurate, specifically in Fluent, and we're really interested in getting a very sharp, explicit interface, so we're going to use that GeoReconstruct method, and I'll show you how to set that up when we get over into Fluent. Our domain today is going to look like this. We're going to be doing a axisymmetric simulation. So you can see our axis in yellow here. We're going to have a inlet condition at the top, which is defined as a pressure inlet, where we're going to put in our pressure profile. You can see our nozzle down here, which is about 100 micron across. And everything below the nozzle is going to be defined as our air region. And on that air region, we're just going to use a simple P = 0 outlet condition. The only other thing we need to discuss is that our simulation is going to be isothermal, so we're not going to be tracking any energy or heat transfer, and we're also not going to track any gravity. In this case, our droplets are so small that the flow is fully dominated by the surface tension and the inertia of the pressure profile, that gravity does not make any impact on our simulation, so we're just going to set gravity equal to 0. So without further ado, let's hop over to Fluent and I'll show you how to set this up. So when we open up Workbench, we're going to use the Fluid Flow Fluent module. And as you can see, I've already pulled that across for our tutorial here. And the first thing we're going to do is set up our geometry. So we'll look at our geometry now. So you need to remember every time you're setting up an axisymmetric simulation in Fluent, your axis needs to be along the x-axis in Spaceclaim or Design Modeler or any other CAD package that you're looking at. So as you can see here, our axis is defined right across the x-axis. So we can see our nozzle here, which is going to be 100 microns across. And we can also see our air domain on the bottom and our fluid reservoir up on the top. Now that our geometry looks good, we can hop over into meshing and see how it looks to mesh this model. So now that we're at meshing, we can look at some of our name selections. So first off, we name the walls of our upper reservoir. We named the front face, or the front face of our inkjet printhead, and we set those independently because we're going to give each of these surfaces varying contact angles, so we want to make sure we set them explicitly. The next thing we have is our outlet on the bottom, so the bottom face and the side face of our air domain, and our inlet up at the top, and then of course our axes along the side. So we can see here that we already meshed this model, and we just used a simple mesh by setting the element size to 5e-6 meters or 5 micron. And you need to remember when you're doing VOF or multi-phase simulation, your simulation time is going to be directly related to how fine of a mesh you're looking at. So you want to make sure that your mesh is fine enough to capture the physics that you're looking at accurately, but you don't want to over refine because it's going to make your simulation time go very, very high. And we'll touch a little bit more on this when we talk about setting the time step and going through calculations of the VOF model. So now that our mesh looks good, we can go ahead and update it, which will transfer it over to Fluent, and we'll go ahead and get started on the Fluent part. So now that we're back in Workbench, we can go ahead and double click on the setup to open Fluent, which will bring up the Fluent launcher. We want to confirm that our simulation is set by default to 2D. We're also going to turn on double precision, and we're going to increase the solver processes to 4. And go ahead and click start, and we'll get over into Fluent. So now that we're in Fluent, we can check that our mesh was carried over correctly. So we can see we have our outlets defined, our inlets defined, and our walls defined correctly. And we're going to go ahead and go through our setup. And as always, we want to go top to bottom. First things first, we're going to double check our mesh. It's always a good habit to get into to check both your mesh and your mesh quality. And both of those look okay. So we're going to go ahead and get started with the setup. So starting at the general tab here, We're going to change to a axisymmetric model since we're doing an axisymmetric model. And we're also going to change from steady state to transient. Next thing we're going to do is set our models. We're going to turn on the multiphase volume of fluid model, and we're going to come back to that in 1 second. We're also going to change our viscous model from the default of SST K omega and go ahead and change that to laminar. So before we go back to our multiphase model, we're going to set up our materials. So we'll come down here to the materials tab. We'll look at our fluid. We can see that air, which is the default fluid, is already defined. We can double click on that. We'll go ahead and jump over to the fluid database or Fluent database. And we're going to select water liquid as our secondary fluid. So we'll copy that over to our case and go ahead and close out of that. So now that we have both our air and water defined, we can hop back over into our multiphase setup and look at our settings there. So these are all the default options when you turn on the volume of fluid, and we're going to keep those the same. So we're going to be using the explicit formulation to make sure that we get a very sharp interface of our droplet. We're also going to keep the interface modeling type to sharp instead of sharp and disperse, which will give you a little bit more of faster simulation, but at the cost of accuracy if you change to dispersed or sharp disperse. So we're going to go ahead and keep those on. We're also going to turn on interfacial anti-diffusion, which can help when you're modeling surface tension driven flows to get a little bit sharper interface as well. Next thing we're going to do is we're going to hop over on the tabs here to our phases tab. And here's where we can set our phase 1 and phase 2. So our primary phase, we're going to set to our water. And we're also going to want to make sure to name this something that's relevant. And you'll see why we do that a little bit later. So I'm going to call it water phase, and I'm going to click apply. And we can go ahead and set up our second phase, which is going to be the air, and we can name that air phase and go ahead and click apply again. Next tab we're going to look at is the phase interaction tab. And under this tab, we can set our surface tension. So we'll go ahead and change our surface tension to constant. We'll put in the surface tension of water to air, which is around 0.072 Newton meters. We're also going to check surface tension modeling, and we're going to use the continuum surface force. There's two options in ANSYS Fluent for doing surface tension modeling, the continuum surface force and the continuum surface stress. Both of them have their kind of quirks and are accurate in some things and less accurate in others. For our case, the continuum surface force is going to give us much better results, so we're going to stick with that. Here we're also going to turn on wall adhesion, so we can set our contact angles of our fluid as it interacts with the walls, and I'll show you how to set that up in a minute. So with that all set, we're going to go ahead and click apply, and we're now done with setting up the VOF segment. So now that we're done with setting up our materials and our models, we'll jump down here to our boundary conditions. So the first thing we're going to want to do is we're going to want to change our inlet condition to a pressure inlet. And we can see here, we can set the total gauge pressure and the supersonic gauge pressure, but we're not going to use that right now. What we're going to do is actually import a boundary profile for our pressure profile. We're going to come down here to File, we're going to Read, and we're going to go to Read Profile. And this profile I wrote by hand to generate just kind of an arbitrary waveform. If you want to do this on your own, you can check out my video on reading and writing boundary profiles, which will give you a little bit of important information on how to set boundary profiles and the right syntax to use when you're doing it. So you can see here we have our inlet pressure for the water simulation. We're going to go ahead and select that and click OK. That's going to go ahead and read in, so we can see that we have 61 points read in the profile correctly, and we have information for both time and pressure. We can take a look at how our pressure profile looks by coming over to the results tab up top here and clicking on profile data. And you can see that we have our inkjet pressure profile. The y-axis is going to be pressure and the x-axis is going to be time. We'll go ahead and plot that. And so what you can see here is a pretty standard inkjet pressure profile for piezo inkjet head, where we're going to ramp up the pressure during the ejection stroke And then we're going to come down quickly and do a negative pressure pulse to essentially retract the droplet and make sure that we have good breakoff. And then we're just going to go to 0 for the rest of the droplet. And we'll see what this looks like when we're generating droplets a little bit later. So now that it looks okay, we're going to make sure that we set the correct pressure profile under our inlet condition. So if we go to this little drop-down tab, we'll now see that we have our UDF and profile listed, and we'll go ahead and select the pressure profile. Click apply, and that's good to go. The other thing we're going to want to do when you're doing multi-phase simulation is you have to tell Fluent what fluid is going to be coming in the inlets and out at the outlets, essentially. And you can do that by expanding your inlet or outlet condition, and you'll see both the water phase and the air phase here. If we go to the second phase here, we can now set the volume fraction of that phase for our inlet. So in this case, we're going to be inletting only water into the top of our domain. So we want our air volume fraction to be set to 0. So that looks okay. We'll go ahead and click apply. And you're only going to be able to set this for one of the phases. So if we look at the water phase here, you're not going to be able to set that volume fraction. And the volume fraction is essentially calculated as 1 minus whatever the other phase is. So since we set the air phase to 0, the water phase is going to be 1 on our inlet. At our outlet, we're able to set the backflow condition, again, just looking at the second phase. And in this case, in the lower part of our domain, we only want air backflowing into our domain. So we're going to set the backflow volume fraction of air to 1, and we'll go ahead and click apply. So the next thing we're going to do is we want to set our contact angles along the wall. And I'll hop back over here into PowerPoint quickly and show you how the contact angles work. So whenever you're doing a multi-phase simulation and you have a fluid and air in contact with a solid wall, it's going to create what's called a contact angle or a wetting angle, which is often referred to. And you can see essentially what that means here is as your fluid sits on that wall, it's going to form an angle, or sometimes referred to as a triple line, between the air, your fluid, in this case is labeled as oil, and your wall. And in this case, it's set to 30 degrees. If we look at the Fluent dialog box here, and we'll check it out again when we hop back over into Fluent, you can see that it lists our first phase, the water liquid, our second phase air, and then a contact angle. The contact angle is always defined as the angle inside the first phase that's listed in this box. So in this case, we have water liquid, and the angle inside that fluid is set to 175, which means in this case, that wall is very non-wetting. So anything over 90 is going to be non-wetting, and anything under 90 is going to be very wetting. So we'll hop back over into Fluent and we'll set that up for ourselves. So in Fluent here, we're going to set the contact angle along two faces. We're going to start with our walls, which are the walls in the upper part of the domain where we have all the liquid. And so in our case here, we can see that our contact angle, we have our air phase as our first phase and our water phase as our second phase. So this angle here is going to be set in our first air phase. In the upper part of our section, we want to make sure that our water is very wetting to that upper reservoir. So we're going to set the angle in the air phase to something very high. So we're going to choose, let's go to 160. And we'll go ahead and click apply. And again, what that means is that the contact angle in the air phase is going to be 160, which is going to make our contact angle in our water phase 20 degrees, which is going to be very wetting. For our front face here, we want to make sure that our front face is highly non-wetting. So in this case, we have our air face first again, and we're going to set that to something very low. So we'll set that to 20. And again, this will mean that the contact angle inside our liquid phase or our water is going to be 160, so very non-wetting. We'll go ahead and click apply. Now that we've set those, we can hop over into our methods here, and there's a few things that we're going to want to change here. So the first thing that we're going to want to change is the pressure velocity coupling. When doing the VOF model, it's found that the PISO, pressure velocity coupling, is very accurate and very fast to solve, and is usually recommended when you're doing a VOF simulation. So we're going to go ahead and use the PISO for the pressure velocity coupling. The other thing that we're going to want to do is use Presto. Presto works very well when we're calculating that variable density, and we're going to want to keep that in check as well. And it should default to when you turn on the VOF model to Presto. So this volume fraction is what I referred to earlier as the interface reconstruction technique. So we can look at the dropdown here. So we can see our GeoReconstruct, our 6SAM, compressive, and modified HRIC. Again, we're going to use GeoReconstruct as it's highly accurate at the cost of a little bit additional simulation time. But in our case, we're looking for really sharp interfaces. We want to make sure that drop is captured very accurately. So we're going to stick with the GeoReconstruct method. Under controls, sometimes when you're doing VOF, it's common to change specifically the density to something like 0.8 or 0.7 if you're having trouble getting the simulation to converge. But in our case, I think we should be fine leaving it at 1. So we'll leave all these under relaxation factors where they are. The last thing we're going to want to do is create our initialization. And you want to make sure you're paying specific attention to your initialization when you're doing multi-phase simulations, because there's a very important step, which is patching what fluid is going to be in what part of the domain. So the first thing we're going to do is, for our case, we're going to use standard initialization. We'll have the gauge pressure and velocity set to 0. And we're going to set the air phase here equal to 1. And what that's going to do is when we initialize our simulation is it's going to set the entire domain equivalent to 100% air. And now what we can do is we can come over to this cell registers area, and we're going to go ahead and create a new region from the cell registers. Our region is going to be where our water is located. So we'll name this water region. And I know from our domain that our water region is going to extend from about arbitrary value of about -1 to 0, and then from 0 to 1 in the y direction. We can go ahead and save and display and see what that looks like. So you can see here what we essentially did was we marked all these cells above the orifice of our inkjet printhead, and we're going to now patch all that region to be our liquid or our ink, in this case water. So we can go ahead and close out of that, and under the initialization tab we can come over to patch. We can go to the phase drop down here and select just our air phase. We're going to patch the volume fraction of our air phase. That region is going to be 0 air or 100% water. And we're going to select our registers that we just set, so our water region, and we'll go ahead and click patch. So now our simulation is pretty much ready to run, but before we ever run a VOF simulation, it's a good idea to check and see what our domain looks like for our initial condition. So we're going to come down here to the graphics window. We're going to create a new contour. We'll call this volume fraction. And we can look at a contour of phases, the volume fraction of the phase, and then choose the water phase as the phase we want to look at. Go ahead and save and display, and I'll show you what that looks like. So you can see now what we have. So in our top part of our domain here, and in our orifice, we have entirely water, so our volume fraction is 1. And then in our air domain, where we just have air, the volume fraction of water is 0. So this looks good, and we're ready to start calculating. The last thing we want to do when we're setting up a transient simulation is we want to make sure that we're saving time steps so we can get those cool videos and get that transient data as our simulation progresses. And in this case, we're just going to use the autosave feature built into Fluent. So we can go ahead and click edit. We're going to change from time steps to flow time. And we're going to save a data file every 1e-5 seconds. Our time step is going to be around 1 microsecond. So this will roughly save every 10 time steps that we do in our calculation. For saving case files, we can leave this on only modified. Sometimes it's good to do writing case files each time, but we'll leave that as is. And we're also going to keep the file storage option just set to the default here, which is deselecting this retain only recent files to make sure we don't lose any data. And the last thing we want to do is check our data file quantities. So essentially what we want to save in our automatic export. So some things that we want to add here, we're going to add some of our pressure variables. We can look at our density as well, so we'll export that. Velocity magnitude and axial and radial velocity will be good to look at. And then if we scroll all the way down to the end here, you can see some of our VOF parameters. So we're going to want to look at, we'll just go ahead and look at all of these VOF parameters. So we can look at the density of water, the volume fraction of the water. Some of the VOF gradients are also good for troubleshooting and everything else. We'll go ahead and click OK on that. Click OK on our autosave. And now we're ready to look at our calculation. So if we come over to the calculation tab, it's always a good idea to hit this little check case option here. In this case, we have no recommendations to make at the time. If you do make some sort of glaring error, this check case option can sometimes catch that, which is good to know, especially when you're getting started with Fluent. And now we're going to change our time stepping method. We can do a fixed time stepping method if we have a good sense of what our time step should be and we want to use a consistent time step throughout the simulation. This can usually give you some very accurate simulations, but will also take a little bit long because you're always going to be using usually the smallest time step that the domain can handle. In our case, to speed up our simulation a little bit, we're going to use adaptive time stepping. And in Fluent, there's a multi-phase specific method for adaptive time stepping, which uses this global courant value to set the time step explicitly. And I'm going to hop back over into PowerPoint real quick and explain this courant number because I feel it's really important when you're doing multi-phase simulation to understand this variable and what's going on. So the courant number is something that you're going to hear about a lot when you're doing multi-phase simulation. And it's often referred to as either the CFL number, the courant number, or by its entire name, which is the courant Fredericks-Lewis condition. And we can see our equation up in the top right here, which is that the CFL is equal to U, which is our velocity in our domain, and multiplied by delta T, which is going to be our time step, which we are going to set, and then delta X, which is our cell size. And the most important thing, especially when you're using the VOF model, is that you always want your courant number to be less than 1 if you want an accurate simulation. Sometimes you can relax this variable to 2, 3, 4, 5, but you're gonna lose some accuracy if you set it anything over 1. And this essentially gets to the fact of why VOF simulations can take a very, very long time to calculate. So what do we mean by this Cmax is equal to 1? What the courant number means essentially is how fast your interface, in this case, is moving across your cell domains. So if we look at this first simulation here, we can see that we have 5 simple square cells here, and we have our interface in red. If our C value is greater than 1 or our courant number is greater than 1, in one single time step, this interface is going to move across all 5 cells and go from your starting cell all to the end in one time step. This would be equivalent to a CFL number of 5. What we really want is a CFL number of 1. And what that means is that our interface for every time step is only going to move one cell at a time. So the two ways that we can change our courant number to play a little bit with how fast our simulation runs is, one, by changing our time step, so our delta T. We can decrease it to decrease the courant number or increase our time step to increase the courant number. We can also play with our mesh a little bit. So this delta X, in our case, it's going to be the size of this square is going to be our delta X. And this is what I was referring to earlier in the meshing, is that if you refine your simulation really, 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 really small, it's going to take a really long time to get this simulation to run because you're only going to be able to move such a small spatial derivative to keep that courant number under 1. So the courant number overall is really critical for setting our time step, and we want to make sure that we're tracking that throughout our domain and setting our time step correctly. And usually Cmax, like I mentioned before, is going to be less than or equal to 1 for an accurate simulation. So now that we're back over in Fluent, let's look at how we can set our courant number and set our time stepping explicitly. So the first thing we're going to want to do, since we're using adaptive time stepping, what adaptive time stepping is going to do is look at that courant number and change our time stepping to be as big as possible without exceeding whatever our global courant number is set to. So in our case, we're going to set our global courant to 1 because we want an accurate simulation. We can now change the duration of the specification method from incremental time steps to total time. And we know we're going to want to run this for about 1 millisecond, so 0.001 seconds. We can also change our settings of our adaptive time stepping down here. And we can see that our minimum time step is set to 1e-5. We're actually going to bump that down to 1e-6. And we're going to set our maximum at about 1e-4 as the maximum time step it can take. And we can leave these step change factors as default. So the other option, which is good to use when you're doing surface tension driven flows or flows like this where the surface tension is really important, is you can switch from using the courant number as your criteria for setting your adaptive time stepping using a physics-based constraint. In this case, we're going to turn it on because we know that surface tension is very important at such a small scale. And this is going to use a slightly different formulation similar to the courant number to set our time stepping and make sure that we're not going to too big of a time steps and making our simulation diverge. We'll go ahead and click save on that. We can set our initial time step. You usually want to start with your initial time step somewhere around your minimum time step. You want to start very, very low in your time step, and the adaptive time stepping will work up as you get there. But when you're first starting the VOF simulation from t=0, there's a lot of calculations that the domain has to do to set your free surface and calculate all your initial conditions and kind of get that steady state going. So it's always a good idea to start with a very low time step for your initial time step. We're also going to increase here the maximum iterations per time step to something pretty large. So in our case, we're going to set that to 50. And we want to make sure that for each time step, we have enough iterations that we can converge. If we set this too low, the simulation can sometimes keep marching forward even when our simulation isn't converged, and it can lead to a buildup of errors over our timescale. So now that everything is set up, we can check this report simulation status, and we can go ahead and start our calculation. So now that our calculation has started, we can see our simulation is getting very good convergence. So we're dipping down very readily and we're hitting our convergence criteria each step. If we look at our simulation status, we can see that our total flow time is slowly increasing. And you can also monitor this time step value up here and see what the adaptive time stepping is doing. So in our case, we are sitting pretty nice at 1e-6. It doesn't want to increase it. And our simulation is converging okay, so we know that our time step is low enough. If you are seeing divergence, so if each of these little spikes is not converging down and the simulation is taking off very readily, you should stop the simulation, try a smaller time step, and come back to it. I would say somewhere around 80 or 85% of the errors I see from students when they're starting with VOF simulations and having trouble always diverging or getting errors is that their time step is just way, way too big. So we want to make sure that we're checking our courant number, we're setting our time step very low if we need it, and going from there. So as you can see, we're only about 55 microseconds in our simulation. So this is going to take a bit of time. I'm going to go ahead and step away, and we'll come back when the simulation is done calculating. So now that we've completed the calculation, we can check out a few things here. Go ahead and click OK and the calculation complete. We can take a look at our time step and total flow time. And as we can see, our time step stayed set at 1e-6 the entire simulation time, which tells me that this simulation using the physics-based constraint method may have wanted a slightly smaller time step. But if we look at our scaled residuals, we were getting good convergence throughout. So we're going to go ahead and continue on with the calculation. First thing we're going to do before we hop over into CFD Post is we're just going to take a quick look at our volume fraction contour that we plotted earlier. As you can see here, you can see one little droplet at the end and some movement in the meniscus, and it looks like our simulation worked as intended. So we're going to go ahead and hop over into CFD Post and do some post-processing. Now that we're in CFD Post, we can start doing some post-processing of our simulation and see how our inkjet head performed. We're We're going to start by going to the default transform here, transform, and we'll deselect instancing info from domain and go ahead and apply a reflection across the ZX plane. This will give a reflection of our axisymmetric surface and give us a 2D projection that looks more like our actual inkjet geometry. Next thing we're going to do is we're going to come up here to the top. We're going to click on the contour, and we'll recreate that volume fraction contour that we had previously shown in Fluent. We'll go ahead and select the periodic, which is the face of our domain. We will select the water phase volume fraction. We'll leave the range on global, and we'll increase the number of contours a little bit to 50. Go ahead and click apply. So what we can see here is the same volume fraction that we saw previously. So you can see there's a little droplet here, which I suspect is probably a satellite droplet. We'll go ahead and check that. Another thing when working with contours in CFD Post, you can change the formulation or the colors of this contour plot by going to the advanced properties on the contour and selecting a different color map. When I'm doing two-phase flow, I like to use the field phase fraction or feels liquid. And if we go ahead and click apply that, what you'll see is it will make it one phase will be all white and one phase will be all blue. And it's a little more logical to look at than looking at a rainbow contour plot for your two-phase simulation. So now let's check out how our droplet was generated. And we can do that in two different ways. We can come to the top here and look at the time step selector. And we can go through and select individual time steps if we want to look at, any specific time throughout our simulation. Or we can also click on this little movie icon here and actually animate the time steps. So we can see we're at our final time step. We'll go ahead and drag that all the way back to the start. And we'll just go ahead and click play, see what it looks like. So what we can see is we're getting a good droplet ejection. We're getting a long tail out of our droplet. And our tail actually ends up breaking up into a few different satellites. And these three satellites in the middle are actually going to recombine on their way down. We have our main droplet, a large satellite droplet, and another satellite droplet coming in behind it. So we can see how that progresses. Looks pretty cool. We can see our meniscus resonance. And these are all kind of things that you would look at if you're trying to do an optimization in the real world. So if we want to save that animation, we can actually stop this, drag back it to the start, and we can go ahead and click Save Movie. And we can select the name, the folder that we want to save it as well as the video format. I prefer MPEG-4, and you can click on Options. We can make sure that we are doing a 1080p video, so we have good fidelity. And we can also go to the Advanced tab and make sure that our frame rate is on 24, and our quality is set to highest. Go ahead and click OK. And now if we click the play button again with the save movie option selected, it will save the animation so we can watch it back later, add it to a PowerPoint presentation, or just save it for our data in the future. So I'm going to stop that there just so we can keep going. So a few things when you're working with VOF simulations is you want to be able to look at the interface, and you usually want to track some of the properties about the interface. So in this case of droplet generation and inkjet, a popular thing to track is how fast the front face or the front edge of the droplet is progressing through time. And there's a few different ways we can do that. The way I like to do it is by using isosurfaces. And we can do that by coming up here to the location tab, clicking on isosurface, and we'll call this VF for volume fraction ISO. Go ahead and click OK. And now we can select the volume fraction for our water phase. And we can go ahead and set a value. So if you're setting a value in a VOF simulation, it's common to set the value to 0.5, which is going to give you an isosurface right between your interface, or essentially right on the line of your interface. And it's going to be a little bit hard to see in our 2D projection here, but if we go a little bit askew, maybe to the backside here, we can check out our isosurface on the back. A cool thing to do when you're working with these axisymmetric models, and specifically when you're doing isosurfaces, is we can actually rotate in 3 dimensions and create what looks like a 3-dimensional droplet out of our isosurface. We'll go ahead and shut off our volume fraction here, and then go back to our default transform phase. And we'll uncheck show reflection and instead use apply rotation. So we're going to apply rotation. We're going to select our principal axis as our x-axis, which is our axis that our simulation was rotated against. We'll select first full circle, and then we'll set the number of graphical instances to 48. Go ahead and click apply. And now what you can see here is something that looks very much like a three-dimensional droplet. And this is really good for visuals if you're presenting data, or even just doing simulation and trying to get a better sense of how your droplet formation progressed. We can also turn off the wireframe up here in the browser to get a little cleaner view, and even turn on maybe something like the walls or the front face up here so we can get a little bit more kind of representation of where we're looking in our geometry. And we can do the same thing here where we can look at a video of the droplet formation with these isosurfaces, which gives you a really, really cool animation of the inkjet behavior and the droplet formation. So that's a cool one to look at. The other thing that isosurfaces are really good for is doing what I was explaining previously, where we want to look at the progression of the front face of our droplet as it moves through time. And to do that, what we can do is we can set up an expression. And we're going to go ahead and create a new expression, and we're going to call this iso x value. And what we're going to do for this is we're going to right click. We can select a function, CFD Post, and we're going to select the max value. And inside that max value, we're going to look at our variables, and we will look for the max value of the x variable. So essentially how far in the x direction our isosurface is moving. And then after the at key, we'll again right click. We'll go to our locations and we'll select our isosurface, our VF ISO. And we can go ahead and click apply. And you can see right now our isosurface is sitting at about 3.7 E-6 meters, or about 3.7 microns out of the orifice, because it's just at the start of the ejection. And now what we can do with this variable is we can actually plot an XY plot and show how our front face of our droplet progresses through time. So we'll come up here to the chart, and we'll call this droplet flight. Go ahead and click OK. And we're going to want to choose the XY transient or sequence. We can give it a title if we want to give it a title, but we're just going to go ahead and jump over to the data series tab. Our data series, we're going to select expression. We can select our ISO X value. And we can come over to the x-axis, and we want to make sure our x-axis is set to time, and then our y-axis is going to be set to our x value. So we'll go ahead and select x, and we'll go ahead and click apply. So now that the chart is calculated, we can see some really cool effects of our droplet formation. So we can see here, as our first droplet comes out, it starts growing and moving away from the nozzle at what looks like a fairly constant velocity. So we can take the derivative of that line to deduce stuff like the velocity, the acceleration of our droplet as it leaves our inkjet printhead. And we can see here these sharp spikes are when our droplet, our main droplet, leaves the domain, and the tracking will start picking up the secondary satellite, and then finally the tertiary satellite as our individual droplets are leaving the bottom of our domain out of our outlet. So that's a really cool way to get some good data, some XY plots, look at the velocity of the ISO value. We can also write another expression and track the velocity of our isosurfaces. And isosurfaces in general, when doing VOF simulations, are really good for tracking the free surface or the interface and getting a lot of good data off of it. So I think I will leave that there. For the post-processing, there's a ton more you can do with CFD Post, but for the purpose of this tutorial, I think I'll leave it there. So that now concludes our tutorial on using the VOF model and multi-phase simulation for inkjet droplet generation. I hope you guys find that helpful, and you should definitely give it a shot. It's a great model if you're just getting into multi-phase modeling or VOF modeling. And I also just want to give one more word of caution. As I mentioned before, multi-phase modeling, and specifically the VOF model, is still a very, very active field of research and quite a challenging model to use effectively and accurately. So try this out for yourself, set up some more models if you want, and get into it. And even read some research. There's some good stuff out there. And if you like the video, make sure to like the video, share the video, and subscribe to the channel. Thanks, guys. Bye.